Hi, my name is Julie Sherlock, and together we're going to go through a combined spectral problem. I am in group 7, or G. All right, let's do this. So our molecular formula is C9H12, and here are our graphs for each of those. This is our IR spectrometry graph, our carbon-13 NMR spectrometry graph, and our proton NMR graph. And we are together going to fill out these three tables and propose a structure. First, I want to go over calculating the degree of unsaturation, because that will help us figure out our proposed structure. With the formula for degrees of unsaturation is 2 times your total amount of carbons plus 2 minus your number of hydrogens divided by 2. And this works for our problem. But if you have nitrogens and halogens, then it's a little different. But ours is simply a hydrocarbon, so we'll keep it simple. When we plug in our numbers, you get 4 degrees of unsaturation. Now, with 4 degrees of unsaturation, this is actually indicative of a aromatic ring or a benzene ring. So I'm already kind of thinking we might have one of those involved in our final structure. Going back to our IR spectrometry graph and taking a closer look. First off, IR spectrometry is helpful in spotting functional groups and telling us, checking to see if a chemical reaction actually took place, to see if what different functional groups are present, and double checking the purity of your compound. In this case, we are going to look for different functional groups present. So, to help us identify our compound. Already right off the bat, working from left to right, I see 3100 peak here. These are peaks, and those are what we'll be taking a closer look at. So this is telling me an sp2 carbon-hydrogen bond is present in my molecule, indicative of an unsaturated molecule. We also have our classic sp3 carbon-hydrogen bond present right around 2900, around 1600. I'm seeing a peak here, medium peak, which it tells me carbon-carbon double bond is possibly present. And around 1500, I see a carbon-carbon peak range, which is present here, a carbon-carbon bond. Moving down, we are looking at our carbon-13 NMR spectroscopy chart. These charts tell us a lot about the carbon skeleton of our molecule. The number of peaks tells us how many distinct carbons are in an environment. So therefore, if 2 carbons are in a chemically identical environment, there will only be 1 signal present. So counting our signals, we originally have 9 carbons. I see 1, 2, 3, that one snuck in there, 4, 5, 6, 7. So I'm already thinking there is a degree of symmetry here somewhere within our molecule. Moving down the chart from left to right, between 200 and 100 is our sp2 region, sp2 hybridized carbon-carbon bond region, and between 150 and about 120 is our aryl region. So this is another piece of evidence aiming towards we might have a benzene ring in our molecule, an aromatic ring. Let's see, right here around 142, well, moving down, we, in our alkyl region, which is usually below 50, but our sp3 region, or area is below 100. However, our alkyl region is usually below 50. We have 3 unique carbons present here. So that is something to take note of, and we will go dive a little deeper when we start looking at my chart that I have filled out. Here we have HNMR, our HNMR graph, and this tool gives us a window into the hydrogen atoms that are present and their neighbors. So this is similar to the CNMR in that it tells us about a specific atom and tells us about unique hydrogen atoms present. But HNMR does tell us a little bit more information about hydrogens. So the integration is these numbers up at top, and that's the area under the area that the signal gives, and it tells us how many protons are in it, specifically are in that environment. So here we have 5 hydrogens, and this is actually our aryl region between 7 and 8. So I'm again thinking we might have a benzene ring here, and it would make sense if our benzene ring had 5 hydrogens attached to it, because our 6th carbon is looking like it might have a carbon chain attached to it, which is moving down our HNMR graph, is what these hydrogens are telling me here. Looking at the splitting in each of these, you can tell they are a little thicker. That tells us about the neighbors of each of these, of the hydrogens in each of these environments. This having about 3 splits, the peaks are, it'll be one less, these hydrogens will have one less neighbor than how many peaks it has. So if it has 3 peaks, then it will have 2 neighbors. And this one down here, I had counted 6 peaks. So it will have 5 neighbors. And this one right here has 3 peaks, so it will have 2 neighbors. We'll dive a little bit deeper into that, looking at the filled out chart here in a second. So moving on. Just re-going over our IR spectrometry. 3100 told me we had a CH sp2 hybridized carbon hydrogen bond, and 29 had a sp3 CH stretch. 1600 had told me that we have a carbon-carbon double bond stretch, and 1500 carbon carbon-carbon single bond sp3 stretch, reviewing our carbon CNMR. 142 was indicative of an aryl carbon with a functional group attached. And then we have 3 carbon-carbon double bonds here, which are on our aromatic ring. This sp3 carbon-hydrogen signal here is indicative of the one closest to the aromatic ring. And then moving down, we have chemical shifts that get lower and lower. Going down to our HNMR, our 5 hydrogen at chemical shift 7.3 with the multiplicity of a triplet is indicative of our benzene ring. Each hydrogen on the benzene ring has 2 neighboring hydrogens. And the 2.6 is indicative of this, the 2 hydrogens present here, and it would be a triplet, lines up with the triplet multiplicity because it has 2 neighbors, and the multiplicity is n, which is your number of neighbors plus 1. So that would give us triplet, seeing that we have 2 neighboring hydrogens here. The sextet here is involves 2 hydrogens, and we have 3 hydrogens attached to this terminating carbon and 2 attached to this carbon here. So that is indicative 1.6 chemical shift with the sextet multiplicity is indicative of these 2 hydrogens, and the lowest chemical shift belongs to 3 hydrogens, is a triplet multiplicity, which makes sense because there are 2 hydrogens here, and plus 1 gives us triplet for these guys, and this is our proposed structure for the given information. Thank you.